So first, I would like to thank the organizers for giving me the opportunity to be talk here. I'm not going to tell you anything about confinement. I will just assume that you have confinement. But I'm going to tell you a bit about a type of non-perturbative quantum field theory with non-relativistic symmetry that one can understand and use to produce results that can be, in principle, checked in experiment. So here's the plan of my talk. I'm going to first tell you about the non-relativistic conformal symmetry, non-relativistic conformal field theories, and one example of such a theory is called fermions at unitarity, which I will define in at least two different ways. And then I'm going to tell you about the application of that quantum field theory in nuclear physics of neutrons and what we call unnuclear physics. So these are the references that on the basis of which I'm giving this talk. The old paper with Yusuke Nishida, where we try to understand the extension of conformal field theory into non-relativistic physics. A more recent paper with Hans Hammer, where we looked at the consequences in nuclear physics, and this more recent paper, which I might have or might not have time to talk about, where we develop a technique of conformal perturbation theory. So let's first look at the Schrödinger equation for a single particle in free space. So this equation has certain symmetry, which we can use to generate from one solution family of solutions. The one trivial transformation is to multiply the wave function by a phase that corresponds to the conservation of particle numbers. So that I call that generator. And there are space-time translations, and there is a rotation. There is also Galilean boost, which we can use to go from one frame to another frame. And in the new frame, the wave function is the wave function of the old frame with the change coordinates, but we have to include a phase factor in the transformation of the wave function by under Galilean boost. There is dilatation. The Schrödinger equation has a scale invariance under which we scale space and time by two different factors. We scale time twice faster than space. And the most non-trivial symmetry of the free Schrödinger equation is this symmetry. So this, we transform time from t to t over 1 plus alpha t. It can be thought of as a combination of inversion and translation, and translation, inversion, and time translation. But we transform coordinates in a quite non-trivial way and compensate. And when you put that into the Schrödinger equation, you can check by direct calculation that this is a symmetry of the Schrödinger equation. If one multiplies the wave function by a certain factor in front. The first factor is just to make sure that the wave function preserves its normalization, but the phase factor has to be picked here so that the equation is still satisfied. These all transformations form a group called the Schrödinger group. So this is the commutator table of the associated Schrödinger algebra. The commutators of two different generators of the algebra give you another generator. So let me just zoom on to some aspect of this. The commutator of the phase rotation of the wave functions and any other operator is zero. So the number of particles is commute with all the other elements. There is a corner of this table formed by the Hamiltonian time translation, the dilatation, and this proper conformal transformation that form a sub-algebra SO 2,1. That will play some role in future discussion. Now, in 2007, Yusuke Nishida and I tried to extend certain concepts in relativistic conformal field theories to non-relativistic case. We asked ourselves a question imagine that we have a quantum field theory that has the Schrodinger symmetry. What we can say about the properties of the local operators in these theories, and then you can extend a lot of concepts to the new symmetry. In particular, if we accept that there is a notion of local operators, then we can classify this local operator by the charge and dimension. So the charge of the operator is defined through the commutator with this operator with the operator of phase rotation. So in the theory that is Galilean invariant, the charge is also sometimes called the mass. And there is a notion of the dimension of the local operator that is defined by commuting the operator with the dilatation. We can also define the notion of primary operators, which are roughly the operators that cannot be expressed in terms of as a time or spatial derivatives of another local operators. More formally, we take the commutator of that operator with the operator of either Galilean boost or the proper conformal transformation and require that it's zero at the origin. So these operators form the sort of the bottom of the yes of the.
Why is the action derivation?
Why
is it diagonal? How do you know that it's not a logarithm?
We don't know. It could be. Yeah, I'm just assuming a simplest. Yeah. We don't know. Yeah. And so if this in many examples that is the case. So if we have the primary operator at the lowest ladder from which we can build up a whole ladder of operators, these operators have the properties that conformal invariant constrain the form of 2-point functions. In non-relativistic field theories, there is a ratio x squared over t that is dilatation invariant, and the 2-point function of primary operator is just the exponent of that x squared over t. In momentum space, this the 2-point function of the local primary operator has the form that looks like the power of propagator of a single particle carrying the mass that is the mass of that operator.
Question.
Yes.
So for this 2-point function, clearly dilatations is not enough anymore. I mean, you need also the proper conformal transformation from this specific function.
You need, I believe you need this to have this exponent. So you need Galilean boost.
Okay.
So that fits actually this one, and the proper conformal transformation is that there is no extra ratio. I think there's no extra ratio h squared over t in front. So this complete form is fixed by this. If and also you need to use the requirement that the operator are primary. Okay, there is a interesting operator state correspondence. In non-relativistic field theory, the dimension we can put correspond into correspondence the dimension of a charge n local operator with the energy of n particles in a harmonic potential with a frequency 1. In other words, if we have a system of n particles in a harmonic potential with frequency omega, the ground state of such a system is going to be delta times h bar omega, where delta is the dimension of the lowest dimensional operator carrying charge equal to n. Maybe I will give you some example later. So the proof of the operator state correspondence is roughly goes through the following steps. First, we notice that the harmonic potential acting on the particle, putting the harmonic potential on the particle simply means adding into the Hamiltonian an operator C, which is the operator of the proper conformal transformation. If we have a theory with psi plays the role of the annihilation operator, that is C is equal to the integral of x squared times the density of particle. And then one can, if we have an operator, local operator, we can act on the vacuum and then evolve that using the Hamiltonian in free space in Euclidean times. That Hamiltonian smear out the delta function of the initial state which we create by acting a local operator. So now, after this evolution in imaginary time, we get a fuzzy, a Gaussian wave function, which can be shown to be the eigenstate of the Hamiltonian of the single particle in of n particles in a harmonic potential. Okay, so let's talk about various examples of non-relativistic conformal field theory. The most trivial example is free particle with the action given by this form. We can show that this is the conformal, non-relativistic conformal field theory. The dimension of the operator psi here is V/2. If we take the dimension of space to be -1 and dimension of time to be -2. And the charge of the operator psi is -1, acting psi on a state reduces the number of particles by 1. A non-trivial example is non-relativistic anyons in 2+1 dimension. One can see that anyons should be scale invariants, because in order to define anyons, we need to know only one dimension less quantity, which is the statistics of the anyons. But we can also show that the anyons are not only scale invariant, but has conformal invariant. And the simplest way to do that is to look at how the wave function of a system of anyons behaves under the proper conformal transformation. You will see that since all the coordinates of all the anyons transform by the same factor, the statistical properties of the wave function of the anyon doesn't change. How the wave function changes under the breaking of two coordinate is preserved. And so anyon, non-relativistic anyon has conformal symmetry. And then the most useful example is the example of spin 1/2 fermions as unitarity. The fact that this system is conformal was first pointed out by men Stewart and Wise in 1999. And the reason why this is an important example, it is because this system can be realized in cold atom experiments and also approximately by neutrons in nuclear physics. One way to define fermion unitarity is to take the free fermion and then include the 4 Fermi interaction. If one do power counting with the dimension of psi to be d/2, we will see that the dimension of lambda is equal to 0 in 2+1 dimension, and the 4 Fermi interaction becomes slightly irrelevant if we go to 2+epsilon dimension. In 2+epsilon, one can compute the beta function of lambda, which is this, and there is a non-trivial fixed point located at lambda star equal minus epsilon. Minus means that the interaction is attractive, and if epsilon is small, then a slightly attractive interaction drives us or put us in the non-trivial fixed point. Non-trivially, the fixed point survives at d=3, and that is what usually called fermions at unitarity. The fermions at unitarity can be defined non-perturbatively at the level of the wave functions. Imagine that we have a wave function of n particles where m plus n particles, where the first m coordinates refers to coordinates of spin-up fermions, and the n coordinates, these refer to coordinates of spin-down fermions. This wave function is required to be antisymmetric under exchange of 2x or 2y's. Now, in addition, we are going to impose another boundary condition on the wave function when one of the x coordinates approaches another y coordinate. So I'm going to require that the wave function diverges like 1 divided by x minus y plus the correction that start at linear order in x minus y. So it turned out that with this requirement on the wave function, combined with the definition, the usual definition of the Hamiltonian, which is the sum of the Laplacian, we have a well-defined quantum mechanics in the sense that the Hamiltonian is self-adjoint. Here we need to ignore the delta function. Whenever we add this Hamiltonian on the wave function, we ignore all the delta function coming out from the point where x, one of the x is equal to one of the y. Then one can show that this boundary condition is consistent with hermiticity of the Hamiltonian. So this is the non-perturbative definition of fermions at unit time. So one consequence of this definition is that we can compute the dimension of charge 2 operator very easily. So in quantum mechanics, operator psi up x, psi down x is an operator that annihilates two particles at the same point, in the sense that the matrix elements of that operator between a two-body state and a vacuum give us just the wave function. But we have just said that if these two particles have different spins, the wave function diverges when x goes to y. And so these operators cannot be defined as written. One can define, however, more precise limiting procedure in which we take psi up at x, psi down at y, and then multiply to x minus y. In that factor compensates for the divergence of the wave function of psi, this wave function at coinciding point, and we have a finite matrix element. So this is the operator that carries charge 2, and the dimension of that operator is not equal to the sum of dimension psi x, psi up and psi down, but actually 2 delta psi minus 1 in 3 dimensions, that is 2. There are also charge 3 operators, and we know their exact dimension. And this is a rather non-trivial problem. In order to solve this problem, one needs to know the short distance behavior of the 3-body wave function when all 3 coordinates stream to a point. That problem was solved by Vitaly Efimov in 1970, and his solution underlies what is now called the Efimov effect. So here we don't have the Efimov effect, but we have a non-trivial dimension of the operator, 3-body operator. The result of the Efimov's calculation is such that the wave function diverges like a distance between the particle to a fractional power, which can be computed exactly with the solution to a well-defined trigonometric function. And the dimension is 4.27. Okay, so in the real world, the non-relativistic conformal field theory is realized approximately by neutron. And the reason is because the scattering amplitude, the scattering length between the 2 neutrons is much larger than the range of the interaction. So there is a range of energy between about 0.1 MeV and 5 MeV, where the behavior of the electrons can be approximated by fermions at unit time. And the consequence of such a behavior is a power law behavior in processes with emission of finite state neutrons. That we call that unnuclear physics in the paper 2021. So let's consider a reaction, a nuclear reaction in which we take 2 particles that collide with each other, so that in the final state we have 3 neutrons, for example, or any number of neutrons emitted that goes almost in the same direction with the same velocity. Then we can see that process as a 2-step process. In the first step, we create a composite object created by the operator in the non-relativistic conformal field theory that propagate for a long time and then decay into 3 neutrons. And the probability of that process will contain 2 factors. One, the probability of the primary process, and then the second factor is the probability of the decay of this object into 3 neutrons. We call that object unnucleus in analogy with Georgi's unparticle. So if we do the calculation, we will see that this implies that the total the differential cross section of this process as a function of the energy of the particle B, we have a cutoff at near the maximum of the energy of the particle B. The behavior of the cross section has to be E0 minus e to the power delta minus 5 half, where delta is the dimension of the operator that creates this neutron. Near the endpoint of the energy of the particle B, all the neutrons are moving in the same direction with the same velocity, and that's why we think that the power law behavior should that comes from the nonrelativistic conformal field theory should come in. One can even compare that with not with the real experiment, but with the theorist experiment. That is the experiment conducted by theorists using very sophisticated nuclear physics, potential interaction, and computer code. And we see that the behavior of the process of the decay of the pionic atoms with the nucleus being a triton into a gamma plus 3 neutron shows power law behavior when the energy of these photons is near the endpoint, near 100, about 130 MeV. Incidentally, this experiment has been conducted in the 1980s, but the precision of the measurements near the endpoint is not enough for us to extract the power. But the theoretical calculation depicted by this dot here seems to fall onto exactly the curve that is predicted by the conformal behavior. Another possible application of non-relativistic field theory is in the physics of the so-called 2-neutron halo nuclei. So some of these are depicted here: helium-6, lithium-11, and carbon-22. Especially carbon-22 is a very strange object. Usually, the isotope of carbon has only A equal to 12. Here we can put 10 more neutrons in the system. Is still bound from the point of view of strong interaction. Carbon-22 decays only through the weak interaction. So each of these nucleus can be thought of as a core that is relatively compact, bounded with 2 neutrons. So these 2 neutrons interact with the core by attractive interaction, but they also interact with each other. And some of these nuclei are interesting because any other 2-body subsystem would not bound, but there is only a bound state of 3 objects. This object can be thought of, roughly speaking, as a charge 2. It's as if you have a non-relativistic conformal field theory, and you put some kind of a heavy defect into this theory, which can form a bound state with a charge 2 mode, but the charge 1 mode doesn't bound on the defect. It turns out that many properties of such a system can be predicted by writing down the simplest quantum field theory of such a system. And for example, we can predict, so this is a graph. It will take some time to explain the curve, but roughly speaking, this is the probability that a photon carrying momentum, carrying energy omega, can break up this halo nucleus. The probability is 0 if the energy of the photon is less than the binding energy, and then quickly grows and then goes down. So all these curves can be computed in an analytic form using the effective field theory.
You mentioned
it's not a bound state. Helium-3 doesn't, when you take helium-3, it can bound 1 neutron, but cannot bound 2 neutrons. Yeah. Medium five doesn't exist. There's a twist on that. But I don't mention that. Okay, so I will come to my conclusion now. So non-relativistic conformal field theory have shown the symmetry, and one important example is fermions at unitarity. It's the theory is approximately realized by neutrons in nuclear physics, and it leads to power law behavior of differential cross sections of certain processes near threshold. Theory what can be a theory of two neutron halo nuclei using as one component of such theory, the theory of the non-relativistic conformal field theory of neutrons. This I didn't have time to talk about conformal perturbation theory, but one can compute correction to the expression that I have shown you using some technique resembling conformal perturbation theory. Let me say that the full powers of non-relativistic conformal field theory is still to be explored. There are many fundamental and also applied questions that has not been addressed. So thank you very much for the attention.
Questions?
Is conformal symmetry related to what one would get from relativistic theory with the light quantization?
So if I compare, yeah, if it is
But just
exact.
to take time to be x plus or something like that.
If time is x, if you do light cone composition, then the charge will be p minus will be the mass, and p plus will be the Hamiltonian.
So
So
would this transformation just follow from the relativistic transformations?
the transformation of the wave function.
Yes, I mean the conformal symmetry which you just
I didn't
explained.
I didn't try, but I think it should.
Okay.
Yeah, I think it should. So in short, if I take a relativistic conformal algebra and select all the operators that commute with one light cone momentum, that would form the Schrodinger algebra in one less dimension, one less spatial dimension.
Curious to know if that is the case, how will the power law become an exponential? I mean, like for the 2-point function.
How it's the power? That's an interesting question. I have to look at that. Yeah.
What would be the conformal symmetry, if I understand correctly, it restricts the potential of the particle, right? It makes it restricts the form of the potential within the particle.
So in the case of the spin, so there are cases where there's one over r square potential that is consistent with the symmetry, but one can have local interaction that also preserve the symmetry. So this local, if I have a local attractive interaction between the fermions and fine tune it to the critical values at which there's a one bound state at zero energy, then we have the symmetry. Delta function fine tune. You have to fine tune the strength of the delta function.
Is there any argument why neutrons should be described approximately as a normal environment?
Should, in the sense that if it doesn't, then something bad happened to us, or there's no fundamental QCD reason that we have to expect that. I think it's probably an accident of the
Find everything scale environment, but there is no dimension for us.
Sure.
Try to understand the similar qualitative argument, which will show that for neutrons, why non-relativistic formal field.
No, I don't believe it's anything than just a accident of nature. For example, if you take any other particle, like two, say, lambda, two like this strange baryons, I think they interact in a normal way with no fine tuning at all.
Last question. So the theory, people have argued that the scale varies plus some sample For some of the class of parts. There's similar actually for our.
There might be, but I'm not, I don't, I'm not aware of, so I'm not aware of the argument, and I'm not aware of a counterexample either, so I'm. So,
Yeah, sorry, maybe I missed this, but can you, with reference to the question that you asked, can you say why you landed on the neutrinos as being,
neutrons.
the neutrons, sorry, as being the correct theory? To exemplify its non-relativistic.
Well, not three, but just any theory. This is the approximate theory I claim to describe neutrons. So with the fine-tuned interaction, describe approximately neutrons that in a certain range. And this is just an experimental fact. We measure the neutron scattering length, turn out to be minus 19 Fermi compared to the range, which is 2 or 3 Fermi. So just an experimental fact.
Right.
Right.
There is a relevant interaction in this conformal theory, which is somehow tuned to theorem.
This is there is this big point has one relevant direction that we are somehow tuned to be rather close to that fixed point.
Just the bilinear.
This is the bilinear of O, it's bilinear of that operator. So this operator O2, yeah, it's O2 dagger O2 has dimension 4, but you need 5 to make it a marginal. So this operator is relevant, and somehow we have fine-tuned that operator coefficient to be near the fixed point.
All right, very last question. Yeah, very good question. In one space dimension, does this symmetry expand to something like W infinity?
No, I don't. It's yeah, no, doesn't seem to be.
Okay, let's thank our speaker one more time.